do not find the very least interrupted. So thank you all for inviting me here tonight. I'm so excited to talk to you about our mycelial planet and the hidden world beneath our feet. If you're not aware, the group of organisms that we collectively refer to as fungi are constantly affecting the way that life happens on our planet. And they've been doing so for the better part of the last 1 billion years. These largely invisible ecosystem engineers perform a variety of essential services for our planet. And tonight, I'd like to talk to you about just one of those services and the underground networks that they help to create. But before we jump into that conversation, I'd like to ask you all a question. What is a mushroom? Anybody have any thoughts, ideas? Don't be shy. There's no right or wrong answers.
A fungus.
There's some really wrong answers. But the flower of the...
It's a delicious food.
It's a delicious food, the flower of the fungi. Some really good answers. Anybody else have any ideas?
Fruity body.
It's a fruiting body. Yeah, it's fruity produce. Anybody else? You guys effectively, like, I don't need to be up here. You can, yeah, everybody can be. Well, everybody is right. Everybody gave the right answer for what a mushroom is. If we take the perspective of the fungus, from the fungus's perspective, the mushroom is its reproductive structure. It's the structure that produces spores that's released into the environment, and then if those spores happen to land in a suitable habitat and germinate, a new individual fungus can develop. So mushrooms produce potential offspring for fungi. But for others that share habitat with fungi, they can be other things. They can be food, they can be shelter, and they can also serve as breeding grounds. And for some organisms, they can be all three. But what a mushroom is not is the fungus itself. Many people think that when they see a mushroom, they're seeing a fungus. But that's not the case. It's not any more true than when you see an apple and you're seeing the apple tree. These are simply the reproductive structures of the actual organism. So if the mushroom is not the fungus, what is, where is it, and what the heck is it doing? Well, if we take a look under these reproductive structures, like our mushroom up on the screen, what we see underneath lies the hidden part of the fungus, and that hidden part of the fungus is called the mycelium. If you've ever rolled over a rotting log, peeled back the bark from a dead tree, mucked about in leaf litter in the forest, and come across this white, cobwebby material fanning out across various surfaces, then you've likely come across the body of a mushroom, or a body of a fungus, the mycelium. Well, at least a small part of the fungus anyways, because much of the time, the fungus resides within its substrate. And by substrate, I mean its habitat, and oftentimes its habitat is actually its food, and it's concealed from our view. That is, unless there is abundance of nutrients above ground, as well as moisture and protection from nature's elements. And then the fungus might just emerge from its habitat and begin to digest and absorb the nutrients from that food source, at least while the conditions are suitable. It becomes, for a brief time, visible to us. But once the nutrients are all consumed, or once the environmental conditions turn for the worse, then the fungus begins to break down those cells above ground and return those nutrients to the main part or the main body of the organism below ground. So it can be really difficult to try and determine how much fungus or how much mycelium is directly growing beneath our feet. So whether the fungus manifests as a mycelial fan, or whether it's producing mushrooms, getting ready to fruit and produce some offspring, it can be really challenging to figure out how much mycelium actually exists. So a lot of folks have asked the question, well, how much mycelium is there? Can we quantify this in any particular way? And there's a lot of really clever folks that have attempted this. And I think one of the most compelling comparisons is if we could actually extract all of the fungal mycelium from just the top 4 inches of the soil across our planet. So if there was some miracle way that we could do this, and if we could line up those cells, one end to the other, they would extend out about 450 quadrillion kilometers. Well, that's a pretty ridiculous number. How much is 450 quadrillion kilometers? Well, to give us some perspective, that's about half the distance of our Milky Way galaxy. So when I say that we live on a mycelial planet, I'm really not over-dramatizing the situation. And tonight, we'll see if we can untangle some of the mysteries behind this underground network of fungal filaments. So let's start off by taking a closer look at how the mycelium develops. As I mentioned, the mycelium of the fungus is made up of cells. These cells are called hyphae, and they're microscopic tubular filaments that extend from their tips and grow out in an ever-branching pattern and these hyphae explore, scavenge, and acquire nutrients for the body of the fungus. But in addition to this primary activity, these hyphae are also competing with other fungi to occupy territory. They are producing chemicals to inhibit other organisms from eating them. There are some that are searching for plant roots to partner with, and there are others that are searching for plant roots to infect. And regardless of the ecology of any of the individual fungi, fungal mycelia in general are constantly interacting, shaping, and altering the physical and chemical, as well as the biological world beneath our feet in ways that we had yet to fully comprehend. In addition to all of these below-ground behaviors and activities, sometimes when the conditions are right, the fungi or the hyphae can begin to felt together in very defined ways and produce structures that we think of as mushrooms. Now, there are certain fungi produce a wide variety of different reproductive structures, which we also call fruiting bodies, sporocarps, and tonight I'm going to use the term mushroom because it's a term that everybody is familiar with. But keep in mind that all fungal reproductive structures are not these nice, beautiful, umbrella-shaped structures. Sometimes they look like corals, or they look like puffballs. They can take on a variety of different features, and sometimes they are produced above ground as well as below ground. But I'll be using the term mushroom for the most part. So these are the structures that produce our spores. And when the spores are released, they land on a suitable substrate with the right amount of nutrients, water, and light. They have the possibility of germinating just like a seed from a plant might germinate. And when they germinate, they produce a single thread of hyphae called a germ tube. That germ tube begins to elongate and branch out, creating this interconnected network of hyphal cells. Now you might think that this, let me find my little, you can see that good. You might think that this is the beginning of our new fungal individual, and it is in some ways, but it's also not, because the cells of this, these spores are actually, they can't give rise to a new individual because it only contains the DNA from one parent. And so this fungus needs to come in contact with another genetically distinct but sexually compatible member of the same species so that their hyphae can fuse. And when that happens, what results is the genetic information from these two fused hyphae combine, and we end up with a cell that, as it reproduces and replicates, will result in an individual, or all the cells coming forward, will have the genetic information from both parents. And so only at this point do we have our new, fully functional, sexually reproductive fungal individual. Either one of those hyphal networks would be unable to produce mushrooms, but since they've mated, this new mycelium is able to produce mushrooms, and it will continue to grow and expand, exploring and scavenging for nutrients out in all directions in more or less a circular or radial pattern. But as the mushroom begins to grow, it becomes very energy inefficient for it to maintain all of those old hyphal cells. So as it grows, it begins to cannibalize and break down the cells on the interior part of the fungal mycelium. And it then reabsorbs those nutrients and passes them along to the ever-growing, ever-expanding outer ring of fungal mycelia. Has anybody in here ever seen a fairy ring? Well, what you're seeing is the leading edge of the fungal mycelium. So you can actually tell how large a fungal mycelium is by looking at the boundaries where the mushrooms are being produced in that fairy ring, because they will only ever be produced in this outer growing edge, leading edge of the fungal mycelium. And of course, once the mycelium has spread more than a few meters, it becomes much more likely that it's going to encounter situations which could disrupt or fragment the mycelium. So if we think of some of our activities that could lead to this, so anything from digging a trench to building a road to tilling our gardens, as well as natural events like floods, landslides, earthquakes, or other organisms that are in the soil or digging up the soil, can all cause the mycelium of the fungus to fragment. And in this example, we can see that, just for demonstration purposes, there are 5 different fragments of this fungal mycelium. And you might think that this is bad news or end of days for the fungus. But fragmenting the mycelium does not kill it. In fact, each one of these separate segments can continue to grow independently. And though they're not physically connected anymore, each one of those is still part of the original individual. So each segment is genetically identical to each other segment. So you might think of these as 5 separate individuals, when in fact they are still one and the same. And at any point in the future, should any of these disconnected fragments come into contact with one another, because they are genetically identical, they can refuse and reform their mycelia. Again, we don't know how, this is all theoretical. It's pretty hard to know whether or not this can actually occur under natural conditions. And in principle, a mycelium can continue to spread through the soil indefinitely, as long as there's enough substrate and enough nutrients. Fungi could effectively be immortal. And we certainly have examples of very large and very old mycelia. About 1,000 or several thousand years ago, a species of honey fungus called Armillaria astoyi released a spore, and that spore settled in the Malheur National Forest in the Blue Mountains of Oregon. That spore germinated, it started to grow and spread, and it has never stopped. Nicknamed the humongous fungus, it is one of the planet's largest living organisms, and it's the biggest ever recorded by area on land. This individual inhabits around, the boundaries of this individual is here in red. This individual inhabits about 3.5 square miles, covering 2,400 acres of forest. This is about the same area as 1,700 football fields, or roughly the same size as Mendon Palms Park. It's at least 2,400 years old, and is estimated to weigh somewhere in the vicinity of 7.5 to 35 kilotons. And while perhaps better known for the edible mushrooms that it produces, functionally, armillaria causes disease and eventual death in weakened and stressed trees and shrubs. And though these pathogens produce some truly immense hyphal networks, these are not the type of networks that I'd like to focus on our discussion tonight. Instead, I'd like to shift our attention to another group of fungi that also use trees, and most other plants for that matter, for food, but they do so in a decidedly different way. These are fungi that form a symbiotic relationship with plants, and this relationship is called mycorrhizae. Let's start by deconstructing the word mycorrhizae. The word myco comes from the Greek word for fungus, and rhizae comes from the Greek word for root. And so we know something with this term alone about the physical construction of this symbiotic relationship. This is literally fungal plant roots. In this relationship, the fungi colonize the roots of plants, allowing for the exchange of nutrients, water, and other molecules. Has anybody in here ever heard of mycorrhizae before? How about the wood wide web? Anybody else? The wood wide web. The wood wide web. You know where I'm going with it. We'll see about that. Tell me at the end whether I took you where you thought you were going. Well, if you've ever heard of mycorrhizae or the wood wide web, then you've likely seen this relationship portrayed as a mutually beneficial relationship between plants and fungi. End of story. But it's not the end of the story, much less the whole story. The plants and fungi associated in mycorrhizal symbioses experience outcomes of this relationship along a continuum. At one end of the gradient, both parties benefit more or less equally from their association. And we refer to this as a mutualistic relationship or as a mutualism. But also, and maybe surprisingly for some of you to learn, that sometimes only one party benefits to the detriment of the other, and this is considered a parasitic relationship or a parasitism. And there are also variations along this gradient, even situations where, though physically connected to one another, neither one of the partners, neither the fungus nor the plant particularly benefits nor is harmed by this relationship. These potential outcomes are highly context dependent, and there are many factors and forces that can influence what outcome the fungus or the plant might experience at any given moment in time. And some of these factors and forces include the life history, life stage, and genetics of the individuals involved, the health of the photobiont, meaning the plant host, as well as the health of the mycobiont, meaning the fungal partner. Seasonal factors can certainly play an important role in these outcomes, as can the soil type and nutrient status of the soil. Competitive factors will certainly drive some of these outcomes, as can any disturbance that the systems might be experiencing at any particular moment. Despite these outcomes not always being favorable for both parties, on average they are. Mycorrhizae have persisted for over 475 million years. That's roughly the same amount of time that plants have lived on land. So I believe it's a fair generalization to label mycorrhizae as a mutualistic, beneficial relationship between almost all terrestrial plants and certain fungi. However, I think it's really important for everyone to understand and to keep in mind that this is an oversimplistic generalization that fails to capture the full complexity of the relationship between these two organisms in their natural environment. As I just mentioned, almost all plants and at least some fungi form mycorrhizae. So let's take a look at who is and who is not forming these relationships. Roughly 93% of all plants and about 2% of all fungi form mycorrhizae. For those plants that don't form mycorrhizae, they fall into some very decided groups and families, and we call these plants non-host plants or non-mycorrhizal plants. One of the families that you might be particularly familiar with is the family Brassicaceae. This family are mustards, are cruciferous vegetables, arugula, radish, horseradish, and cresses. As far as we know, there's not a single plant in this family that forms mycorrhizae. The same is true about our sea heaths, our carnivorous plants, and our pinks, or the members of the carnation family. And at one point, we thought that all members of the amaranth, bromeliad, and sedge families failed to form mycorrhizae, but that's turned out to be not to be the case. And it's not clear why sometimes they do and sometimes they don't, but I would put these three families into the sometimes do not form category. So now that we have at least a little idea about who is involved and some of the factors that can influence why they may not always be positive outcomes for this particular symbiotic interaction, let's take a closer look at what occurs between fungi and plants involved in mycorrhizal relationships. And let's start off with our plants. Plants are autotrophic, and by autotrophic, I mean self-feeding. How do plants feed themselves? Photosynthesis, A+ answer over there. Photosynthesis. Plants produce carbohydrates via photosynthesis. And I've abbreviated carbohydrates or sugars with carbon here. And they're able to share some of the excess carbon that they produce directly with fungal partners. In fact, up to 20% of a plant's carbon can be captured or used by its mycorrhizal fungal partner. And that's good news for the fungus, because unlike plants, fungi are heterotrophic. And heterotrophic means other feeding. Like ourselves, fungi have to eat other organisms, their products, their wastes, or their remains in order to meet their energy requirements. So this carbon comes in pretty handy. And in return for receiving that carbon from plants, fungi are able to provide to the plant water and some nutrients like phosphorus and nitrogen. In fact, in certain circumstances, up to 80% of a plant's phosphorus needs can be met by the mycorrhizal fungus, as can up to 25% of its nitrogen needs. Now I can imagine, and you please correct me if I'm wrong, that it's probably very clear why the fungus needs the plant, right? They have a direct line for carbon, something that they can't make themselves, and they don't have to go really out looking for it very differently. They don't have the difficulty to find it. They just have to find a plant to associate with. But why does the plant need the fungus? Aren't they both residing in the same habitat, in the same soil, when they both have equal access to the nutrients as well as the water? Well, that's not really the case. Fungi in general, but mycorrhizal fungi in particular, has some unique characteristics that allow them to access nutrients and water in ways that plants simply cannot. In this image, it may be rather difficult to distinguish between the plant's roots and the fungal mycelium. So I've highlighted the plant roots in orange. The first of three characteristics that I'd like to share with you that make fungi such good scavengers and acquirers of nutrients is that fungi in general are highly enzymatic. And what I mean by that is they produce enzymes and release them out into the environment so that they can digest their food first outside of their body. And they're able to break down all sorts of things. They can break down coarse woody debris, they can break down and digest rocks. So they're able to turn insoluble compounds into soluble nutrients, and then they can ship them directly back to the plant. The plants are not able to break down these substances. They lack the enzymes to do this. So even if they're surrounded by technically tons of potential food, if it's not in soluble form, the plants can't access it, but fungi can. Next, unlike plant roots, the fungal mycelium is not limited in the size that it can grow. We call this sort of growth indeterminate growth. Plants can have a very specified size that they can reach, both above ground and below ground. So the fungi that can grow meters and meters out in any direction can access nutrients and increase the volume of soil that can be explored for nutrients by 2 to 3 orders of magnitude. This becomes pretty invaluable for plants that can't move. We don't think of fungi as being mobile because they're not mobile like animals are mobile, but fungi are in fact mobile organisms. Plants, on the other hand, not so much. They're pretty much stuck in place. So being friends and partners with an organism that can get around and can break down nutrients is a really huge advantage. The third characteristic, is that the hyphae that make up the mycelium are microscopic. And because they're microscopic, they can penetrate more tightly aggregated soil particles than macroscopic roots or root hairs. Plants are literally constrained from accessing nutrients that might, again, be in very close proximity by the physical size of their roots and root hairs. And so if we take a look at, we do a comparison between a microscopic root and a tiny root hair, which is it's blown up pretty large on the screen, but they're still really tiny. The hyphae are about 1/10 of the diameter of a fine root hair. So this means that the hyphae can infiltrate and access nutrients that plants simply cannot. They are able to weave around in and out of small tiny pores, all the while breaking things down along the way. And just to give I'm a fan of perspectives. To give you an idea of kind of the scale of difference here between the size of a root hair and a hyphae, it would be the same as comparing a golf ball to a BB pellet. If you've ever dropped BB pellets or had kids that drop BB pellets, you know you'll never find them all because they get into every little crack and crevice. You drop a bunch of golf balls, that's inconvenient, but you'll find them. You'll find them quickly. So hyphae are very, very tiny and can access and penetrate things that the below ground surface in ways that the plant roots cannot. But plant roots are certainly capable of absorbing nutrients, but they're restricted to where they can absorb nutrients. And that first 5 millimeters or so, it's not very far from the root surface, is about the distance that they can access nutrients. And if those nutrients aren't replenished fairly regularly, you end up getting this zone of depletion. So again, even if there's nutrients right next, just a few more millimeters away, the plant's not able to acquire them. But for plants that are able to form mycorrhizal relationships, they have now friends that can go out and find nutrients, because the fungi can send out exploratory hyphae from the surface of the colonized roots for potentially many meters. And this increases the pool of nutrients that are now available for both the fungus and its plant partner. So I hope you have a little better understanding of how fungi acquire nutrients and water for their plants, for the plants that they partner with, that would otherwise be inaccessible for those plants. So how are we doing? Does anybody have any questions? Yes.
So, I'm wondering why some plants do not form a mycorrhizal root, because it seems like it would be an evolutionary advantage.
That's an excellent question that I have no good answer for. I'm sorry. You're right. Why do some plants are capable and others, most of them do, right? Why do the small percentage do not?
One thing would be that insectivores, I forget what the term they used, the plants, they eat insects because they can't
Carnivorous plants.
get the nitrogen. So they're eating the insects, so they don't need to make the mycorrhizal root.
Right, and that to me is the most straightforward. That's a clear connection. They have access to nutrients by the means of eating other things, right? So they photosynthesize a little bit, and they also eat other things that they trap. So the mycorrhizae aren't as necessary. But for plants like the brassicas, so cabbages and broccolis and turnips and stuff, to me that there's something else going on, and I personally don't know what that something is, but there's an answer to that question. I just don't know what it is. Did you have a question?
Can you introduce hypha? Can you introduce it to the soil?
Yes, and there are industries out there to do just that. You can buy mycorrhizae online, but thank you for this question, because I'd like to give a word of caution. So you could buy mycorrhizae from a variety of different sources. And these sources might be from different parts of the country, different parts of our planet, and they're not well adapted to this environment. I would say you're much better off getting native soil and introducing that to your garden, for example, than buying something, a kit or a package of hydrolyzed mycorrhizae from a vendor anyplace else in the country. You don't know. There's been several. What's that?
What you get. But could you introduce, I ran into a fellow on Sunday, the Rice Market. He's a naval master scientist. He was a mushroom scientist. And he had plastic bags full of $100. And then the mushrooms coming out of it.
Oh,
I asked him the question, is there any use for what's in that bag?
well, those are two different things. So at least I believe there's two different things. So if there's mushrooms that you can grow for food, and they grow it on straw or wood chips or logs and things like that, and those are decomposers. So when that material is spent, when the fungus has consumed all of its nutrients and it produces its mushrooms, and you cut all the mushrooms off and cook them, you could use that material that's inside for compost. You could compost it.
You can introduce it to the soil.
You could see if it, that would be kind of a vegetative propagation. So if you put the mycelium as opposed to the spores, but they're probably, typically they're woody decomposers, so they wouldn't do so well probably in the soil. Yeah, you could try them in mulch, you can try them in coarse woody debris on your property. You can buy what's known as club spawn, and you can inoculate those into cut trees and things like that to produce more mushrooms. But those are different than mycorrhizae.
Well, that'd be different than basically for flower gardens. Things like that.
Yeah. Yes.
So does a single mushroom make both male and female spores?
That's a great question too. Fungi are, I think, the best examples of non-binary organisms. They don't have, by and large, they don't have gender. There are some examples, because as we'll see tonight, there's always examples of everything that I say that will break the rule that I just said. But by and large, fungi are sexless. there are some fungi that have 28,000 different sexes. And so, yeah, that just means anybody you meet becomes a potential mate, right? So, but no, by and large, you don't get, it's not like flowers where you can have the male flowers and the female flowers, or the same male and female in the same flower. They are, we refer to them as compatibility types, just because they can be so varied. 28,000, it's kind of hard to, you lose track. Yes.
Are there any fungi that live in the ocean or in lakes?
There are aquatic fungi. I've never seen them personally, but yes, there are mushroom forming, so there are fungi in all aquatic systems. They tend to be more of the microscopic types, like things like yeasts, which are also types of fungi. But actual mushroom forming fungi, those are relatively maybe in the last 15 years or so. I don't believe that they occur in saltwater environments, but in freshwater environments, I believe, unless I have that incorrect or reversed, you can find fruity bodies in submerged aquatic environments. It's pretty cool, yes.
Didn't we say that 2% of fungi are microrhizal? What about the other 98%? Are you going to talk about that?
If only I had 3 more weeks to talk to you. So, no. I wish we had more time. But yeah, fungi fill a lot of these roles. But tonight, I'm sorry, we'll just have to dedicate to microrizing. Some other night, maybe.
Okay, is it true or false? Well, I've heard people say you can pick the fruiting body and you cut it off with like a knife and leave the root ball alone. And others say leave it alone.
I would say both are right. And I'll tell you, I'll explain what I know and what my personal approach to these things are. So, when you remove a mushroom or a fruiting body, it's effectively like picking an apple off an apple tree in some ways. You're not hurting the apple tree by picking the apple. The apple is being produced in order for something to come and take it and spread the seeds, right? That's kind of the point. But when it comes to fungi, and it's true with other fruits as well, that we need to be, I think, a little bit more mindful in how we approach these things, because we are not the only ones that utilize mushrooms. As I mentioned, they can be food for other species in the environment. They can serve as shelter, and they, most importantly, can serve as breeding grounds for insects. So these things can have cascading effects. So when I hear people going out and saying that they, completely removed every mushroom that they've come across, every morel or every chanterelle or every bolete, I encourage people to give pause, because let's leave some behind for the other. We really like them. I love them. But do we really need them? Some might argue that, yeah, we really need them. We have just as much right to those structures as anybody else or anything else. But if we're not careful, if we all take that attitude, then there's nothing left for anybody. And we start seeing systems collapse. So if you're a mushroom forager, I am a mushroom forager. I forage for a lot of different things. I would just take the approach of being mindful of other species that we share this planet with, and take only what you need and leave enough for other beings as well. That's my personal approach. Yes.
I assume there's different species of mycorrhizal fungi. Do they associate with specific species of plants?
You would think that I had planted her, because this is exactly where we're going right now. So yes, thank you very much for launching me into our next segue of topic here. But before we get right into that, I want to talk about what are the defining characteristics of mycorrhizing. So what features or characteristics do we use to put one mycorrhiza in this bucket versus another mycorrhiza in this bucket? They're pretty straightforward. I've talked about two of them so far. The first is the photobiont, and that's the plant host. The second is the microbiont, or the fungal partner. And the third is the strategy that the microbiont uses to colonize the roots of the photobiont. Collectively, all three of these components are required in order for mycorrhizing to occur. You take any one of these things out, and you don't have mycorrhizing. So let's start off by talking about ectomycorrhizing. Ectomycorrhizing occur in about 2% of all of our plants. The photobionts include all members of the pine family, and that's not only our pine trees, but that's our spruces, our firs, our true cedars, our larches, as well as our hemlocks. And in addition to our pines, our pine family members, beeches, birches, chestnuts, hickories, lindens, and oaks also form ectomycorrhizing. Roughly 20,000 different species of fungi enter into partnerships with these trees. And in addition to forming ectomycorrhizing, the most defining feature of these fungi is that they form either above-ground mushrooms, or mushroom-like structures or fruiting bodies, or below-ground reproductive structures like truffles. So, truffles are a different sort, but they are, in fact, mycorrhizal. Pretty evident that they're directly associated with the plant roots. And when the ectomycorrhizal fungi colonize the roots, the hyphae penetrate the cortex of the root cells, or they penetrate the cortex of the root, but not the cells themselves. This is where the ecto comes in ectomycorrhizing. Ecto means outer or outside, and what's outside are the hyphae. They are surrounding the plant root cell, the cortical cell, in a layer of hyphae called a hartignet. The hyphae also surround the exterior of the roots, kind of blanketing or ensheathing those roots in a layer of hyphae called a mantle. So, a quick summary for this type of mycorrhizing is that ectomycorrhizing is a type of mutualistic symbiosis that occurs in some trees that form partnerships with mushroom-forming fungi that colonize plant roots to exchange nutrients without penetrating the cells of the plant. This is going to be pretty different compared to the next group, which are our endomycorrhizes. Endomycorrhizes occur in about 90% of all of our plants, a wide diversity of plants at that. Everything from herbs and grasses to our food crops, to fruit trees and some of our forest trees, as well as shrubs and flowering plants. Because of this diversity of plants that are associated with endomycorrhizing, as well as some of the structures that the fungi form, there are three subcategories of endomycorrhizing. The first subcategory are our ericoid mycorrhizing. They form in about 1.5% of all of our plants and almost 100% of our ericaceous plants. Ericaceous plants would be plants like heather, huckleberry, blueberry, rhododendron, and azalea. So a lot of common plants you can see in the forest understory. Only about 150 microbiomes associate with our ericoid plants, so a much smaller number than the other group. The ectos are some of the groups that I'll mention in just a little bit. And there are a few exceptions, but by and large, ericoid mycorrhizing, as well as any other type of endomycorrhizing, these do not form mushrooms or any other macroscopic reproductive structures. And because they are endomycorrhizing, meaning inside or inner, they do form structures inside the cells of roots. They form these tightly coiled structures, and they're coiled because this increases the surface area for nutrient exchange. So more nutrients can be exchanged more quickly between the plants and the fungi because there's more surface area within those cells for that to happen. The next type are orchid mycorrhizae. Orchids are our second largest plant family, comprising about 10% of all of our plants. And 100% of orchids, at least at some point in their life, form mycorrhizae, specifically orchid mycorrhizae. About 25,000 different fungal species associate with our orchids, and none to my knowledge form any sort of macroscopic fruiting structure. Like the aerocoid mycorrhizae, they penetrate the cells, forming this tightly coiled structure, and before you ask, I don't know why this is called a peloton and the other one is called a coil. I'm sure there's a very good reason. I just don't have what that reason is. And the last sort of endomycorrhizae are our most common and the most ancient mycorrhizae are our arbuscular mycorrhizae, which form with 78% of all of our plants on our planet. About somewhere between 600 and 1,600 different species have been estimated to form arbuscular mycorrhizae. And certainly in this case, there are no mushrooms or other sort of fruiting structures that are formed by arbuscular mycorrhizal fungi. And they too also penetrate the cell, but the structure that they produce is very different than compared to either the orchid or aerocoid mycorrhiza. They produce these highly branched tree-like structures known as arbuscules. So it's more of a challenge to summarize endomycorrhizae than ectomycorrhizae because of the diversity of plants and the different types of structures, but I've taken a crack at it. And if I were to try and describe endomycorrhizae in a very general way, I would say that endomycorrhizae are a symbiotic relationship between plants that form with non-mushroom forming fungi that do penetrate the cells of their plant hosts. Generally speaking, whether we're talking about endomycorrhizae or ectomycorrhizae, both the plants and the fungi involved in these relationships tend to have high fidelity for the type of mycorrhizae that they form. By that, I mean that a maple tree will only ever form endomycorrhizae with an endomycorrhizal fungus. Taking the fungal perspective, the fungus Boletus edulis or porcini will only ever form ectomycorrhizae with an ectomycorrhizal plant. This is a good general rule to apply. However, what are rules if they're not meant to be broken? Oh, I forgot to mention, sorry. Here are a list of some of the trees that can form arbuscular mycorrhizae in our native forests. So while we tend to think of ectomycorrhizae as our tree fungal associates, arbuscular mycorrhizae certainly will form with quite a number of our native trees. Yes?
I hate to do this, I know you have more for us, but we have to stick to a schedule.
Oh, sure.
And I think you're fine until we're all ready. I didn't want to say anything, but
No, I'm glad.
this has been wonderful. We'll have to put a pin in it, and maybe we can have you back to keep going another time.
That would be great. Thank you.
Thank you so much.
Sure.